Today we are going to be talking about the frequency response of the common gate amplifier. And it is my hope that we will finish up both the low frequency and high frequency response for this circuit today. So we are going to start with our low frequency response. And our circuit of interest will be the fully biased common gate amplifier. So something along the lines of this. Here we have some resistor RD. For a common gate amplifier, we always take our output voltage at the drain. I'm going to have some input capacitance Cin. We're going to take into account if there is a signal resistance R sig. Here is where our input voltage is applied. And we have resistance RS here. And on the right-hand side of the circuit, we have a fairly straightforward resistor biasing network. Let's call this R1, this guy R2, and up here we will have VDD, okay? So how does this really differ from the fully biased common gate amplifier that we dealt with in 335? Yeah, the capacitor there is no longer short circuit. That's literally the only difference, okay? So what I'm going to do is I'm going to call this node X. And we are going to find our transfer function as, since this is low frequency, I'm going to explicitly state H low as the ratio of V out to Vx multiplied by the ratio of Vx to Vn, which is exactly what we did for the mid-band gain in 335, okay? The only change, as Luke correctly recognized, is the fact that we are now going to have some capacitance impedance to deal with, which is simply in series with R sig, okay? So, who remembers what the V out over Vx relationship is for a common gate amplifier? You guys have notes and stuff too. Always look it up. All right, this is taking too long. So the answer is GMRD, okay? So for a common source amplifier, the voltage gain for the common source core amplifier, the voltage gain was negative GMRD. For a common gate core amplifier, the voltage gain was positive GMRD. The presence, so if we're ignoring Bn, R sig, and Cn, if all of this were open circuited, the presence of this resistor Rs with the voltage Vx, they are directly in parallel, so this voltage does not affect the transfer function between node X and V out. Resistor R1 and R2 is just a resistor resistance at the gate, which also doesn't affect anything. So it's literally just GM times RD, which is the same as a core common gate amplifier. Okay. So we have that GM-RD, our mid-band gain already given to us, wrapped nicely in a bow. And then we have a voltage divider here, right? So what do we see looking down? Obviously, RS. What do we see looking up? So if we're looking up at node X, we're looking into the source terminal. And for all of these, we've been neglecting channel length modulation. So let's continue to do this. So what happens when we look into the source of an NMOS transistor? There we go, 1 over GM. That's awesome. Wonderful job. So we have a voltage divider. And then at this point specifically, we see RS in parallel with 1 over G. Okay. So bear with me here. Our transfer function, H of S, is GM RD, because that's VX, or excuse me, V out over VX. And then we have our voltage divider relationship, where we want the voltage drop over RS in parallel with 1 over GM. So that's going to be in the numerator. And in the denominator, we are going to have R sig plus 1 over SCN plus RS in parallel with 1 over GM. Are you guys okay with this voltage divider expression here? Anything seem wild or wacky? Because we're about to mess with it a little bit. So to clear my fraction and more easily identify my pole, as it turns out, I'm going to just multiply by a factor of SCN over SCN dot.
What's the subscript on the R?
S. RS in parallel with 1 over G. Because that's what we see at node X looking down in parallel with what we have looking up. So if I multiply through by a factor of SCN over SCN, what I get is GM-RD multiplied by SCN times RS in parallel with 1 over GM divided by 1 plus SCN times R sig plus RS in parallel with 1 over GM. So from this, what's the frequency of my zero? I look to the numerator. 0. Absolutely right. What's the frequency of my pole? 1 over all this garbage right here. Absolutely right. And so the absolute value would just be 1 over Cn times R sig plus RS in parallel with 1 over Gm. Okay, so our low frequency analysis is done. That's literally it, okay? I want to point out something here, though, that's rather interesting. Our zero and our pole are contributed only because of the presence of this network right here, okay? So effectively, we have a zero and a pole associated with that input capacitance because of the effect that it has on the transfer function, all right? If we went back to what we talked about in our high frequency analysis of the common source amplifier, using the Miller effect explicitly to break that feedback capacitance up to a capacitor at the input side and a capacitor at the output side, we could take that transfer function and easily associate a pole with each capacitance as well, okay? So that is one way in which we can analyze these circuits here. Okay, we only have a single capacitor, so it makes sense here that we should have a single pole. If we had some sort of capacitive coupling to a load resistance at the output, we would wind up introducing another pole into our transfer function, right? We could analyze that either using a direct approach like this, where we literally just break our transfer function up into stages, or we could literally throw away all of this and just look into this network effectively and see what resistance is seen from this point, what capacitance is seen from this point, and then use those pieces together to figure out what our poles and zeros are going to be. So it's effectively very similar to the short circuit time constant method. We'll get into that. It'll be a little bit more, there'll be a little bit better description of what I'm talking about when we have more than one capacitor to deal with, okay? So this was our low frequency response. Let's move along to our high frequency response. All right, so for our high frequency circuit, again, we're going to have VDD up here. Here is RD. So between our drain and gate, we know we should have some capacitance CGD. Between our gate and source, we have a capacitance CGS. Between our source and the bulk, which is at ground, we have a capacitance CSB. So this guy effectively shows up in parallel to our resistor RS. On this side, I still have my resistor R1 and my resistor R2. I have my drain body capacitance, CdB, that I need to take into account. So I'm going to do that over here. So here's my output terminal. Here's CdB. And then here's my input terminal, Vin. Is my signal resistance RC. So just to be clear here, our capacitor Cin that we had in the previous example, we are now at a frequency high enough to where that capacitor appears like a short circuit. We are now in the range of frequencies at which the internal parasitic capacitances of the MOSFET are beginning to influence the behavior of our circuit. There are 4 capacitances, one of which occurs between the gate and the drain. So I put a capacitor CGD between the gate and the drain, another of which occurs between the gate and the source. So that's why we have this CGS. Then there's one between the source and the body, where the body of a NMOS transistor is always assumed to be at ground. So that's why we have this guy here. And then another between the drain and the body, where again, the body is at ground. So that's why we have this guy here. Okay. So what simplification? Yes.
What's the subscript on the capacitance next to the out? It's kind of like the crack.
dB, because it's between the drain and the bulk loop. So it depends on the size of the internal capacitances as to when they stop looking like open circuits. So that's really as good of an answer as I can give you. Typically speaking, these capacitors are on the size of femtofarads or smaller. Okay. So relatively high, but we honestly can't determine what that frequency is until we figure out what the poles are. All right. Okay, so this circuit can be simplified to some extent because I agree with what I think most of you are thinking right now. Oh, good God, this looks terrifying. Okay. So one of the biggest simplifications that we can make to this is by understanding what's going on at this node, our gate. So what's going on at this node? Is a voltage divider circuit. You're absolutely correct. So is this node at a DC quantity? Yes, absolutely. So this node is an additional AC ground, right? Because the only thing that's happening at this node is that the the power supply voltage VDD is effectively being split up to apply some fixed voltage at our gate to make our transistor operate in saturation. That's literally it. So with this node as an AC ground, CGD is now between the drain node and ground, so it's in parallel with CDB. CGS is now between the source node and ground, so it's in parallel with CSB. So this. So here we have RD. I'm grounding my gate node. Here is VN. Here's our sig. And then from here, I have RS. RS is in parallel with CSB. And because our gate is at ground, CSB is in parallel with CGS. On the top side here, I know between my drain and ground that I should have CGD. And because CDB, actually, sorry, I should have CDB. And then because my gate node is at AC ground, I will also have CGD. And here is VF. So this is a simplified view. Let's actually take it one step further. One more simplification here, okay? I'm going to call this arbitrarily node Y and this guy node X. So I'm going to call this ZY, which is literally just RD in parallel with 1 over S CDB plus CGD. I'm going to call this impedance down here ZX, which is simply RS in parallel with 1 over S CSB plus CGS. And then finally over here, I have R sig and Vn, and here is the out. We can analyze this effectively in the exact same way as we did our low frequency analysis, because it's the same circuit, where we've just lumped everything into impedances, right? So our transfer function H high of S is going to look like GMZY, where ZY is taking the place of RD as we had before, because we're taking this whole impedance to be playing the role of what our drain resistance was previously, multiplied by our voltage divider equation, right? The transfer function between, so if this is X and this is Y, the transfer function between Vn and Vx is just that simple voltage divider, where we're going to see, we want the voltage drop over Zx, which is what we see looking down, in parallel with 1 over Gm, because that's what we see looking up. So we are going to see Zx in parallel with 1 over Gm divided by R sig plus Zx in parallel 1 over Gm. This is our transfer function. All right. Now, this isn't of the nice and pretty form where we have our mid-band gain multiplied by frequency dependent parts. We're about to expand it into that, okay? But what I want to suggest here is that, is what I was talking about previously, okay? We have an impedance connected here, which is going to contribute. So some frequency dependent impedance here because there's capacitances rolled up into ZX. So we're going to have a pole that's associated with this node X. And we have a frequency dependent impedance up here that's associated with our output node. So we're going to have a pole that's effectively associated with ZY. And what we're going to find, if I have enough time, is that we can take our big picture transfer function, GMRD times frequency dependent stuff, or we can simply look at the impedance connected with node X and associated a pole with node X, look at the impedances connected with node Y, associated pole with node Y, and we're going to get the exact same result. And that's true anytime we don't have an impedance linking those two nodes. So it's why it worked absolutely like that with the Miller approximation for our common source amplifier. But when we didn't have that Miller approximation, we couldn't associate a pole with a node because our nodes were linked together. Okay. So let's break this thing down into a more formal transfer function. Okay. So the first thing that we're going to look at is that GM ZY. Okay. So GM ZY is GM times RD in parallel with 1 over S CY, which is the same as, let's see, so we're going to have GM times RD over SCY divided by RD plus 1 over SCY. Are we all okay so far? Doing those two elements in parallel. I'm going to multiply by SCY over SCY to clear these pesky fractions. And that's going to look like GMRD divided by 1 plus S RD CGD plus CDB, where CGD plus CDB is just CY, the capacitance associated at node 1. So out of this portion of the transfer function, which again is only associated with that topmost node, oh, we have a mid-band gain that fell out, and we can tell what one of our pole frequencies is going to be. All in one little go. Okay. For the other portion, the voltage divider portion of our transfer function, it's going to take a bit of work. So we have ZX in parallel with 1 over GM divided by R sig plus ZX in parallel with 1 over GM. Okay. Well, as an aside here, so I'm going to put a line through this. ZX could be expressed as RS in parallel 1 over SCX. Right? I had something really similar to that here. So I'm going to jump a couple of algebraic steps ahead and say that RS in parallel with 1 over SCX is going to look like RS over 1 plus S RS CX. It's literally the same algebra, just don't want to do it twice. Where CX is, I'm going to leave it as CX for now because I did it in my notes and I don't want to mess things up. Okay. So we're going to make that substitution here shortly. But first, so this is going to look like ZX over GM times ZX plus 1 over GM. And then down here, we're going to have R sig plus that same thing. ZX over GM times ZX plus 1 over GM. And now further algebraic manipulation. So this is going to be CX divided by 1 plus GMZX over R sig plus ZX divided by 1 plus GMZX. And I'm going to multiply through by a factor of 1 plus GMZX over 1 plus GMZX, which gives me ZX divided by ZX plus R sig times 1 plus GMZX. Now I'm going to substitute in this relationship for ZX. And so, giving myself enough room down here, in my numerator, I'm going to have RS over 1 plus SRS CX and in my denominator, I am going to have RS over 1 plus SRS CX plus R sig times 1, which I'm going to express as R sig times 1 plus S RS CX over 1 plus S RS CX plus GM times ZX times R sig. So that's going to look like GM times RS times R sig divided by 1 plus S RS CX. And since I have common denominator for literally every term here, all of those are going to cancel each other, right? I have the same common denominator in the denominator of this fraction as I have in the numerator. All those parts go away, and we are left with RS divided by RS plus GM RS R sig. That's coming from this third term here. Plus R sig plus S RS R sig CX. The algebra there. Okay. So this RS comes from this term, canceling out the denominator. The GM RS R sig comes from this term and canceling out the denominator. Then I have R sig times 1, which is where this guy comes from. And then I have R sig times SRSCX, which is where this guy comes from. So I have my two different parts of the transfer function. So H I of S is going to be GMRD times 1 over 1 plus S CGD plus CDB times RS over this big huge thing, RS plus R sig plus GM RS R sig plus S RS R sig CX, where, let's see, CX was, I'm gonna have to look at that one, CSB plus CGS. And so it's now in the form that I can tell what the poles are, ostensibly, okay? So we're gonna have a pole associated with that voltage divider at the input. So I'm calling that pole omega Pn. So the pole of this guy is the value of S that will make this whole thing 0, right? Typically speaking, we have it in the form of 1 plus S blah, blah, blah. So effectively, this bit right here is going to be our denominator. And then this bit right here is going to wind up in the numerator so that it cancels correctly. Abdullah.
Shouldn't be there in R8. 1 plus S RD.
Is that the one? So if we look at our first bit here, we have GMRD over this. So that's our GMZY term, right? So I split it out into GMRD times 1 over that to make it very explicit that we have the form that we're used to here. Excuse me, where we have our mid-band gain multiplied by frequency dependent components that tell us what our poles and zeros are.
Oh, yeah, there's also another RD.
Oh, S times R. Okay, I see what you mean there. Okay, I got you. 1 plus SRD. That's where you were talking about, right? Yes, thank you. Absolutely correct. Thank you so much. I actually missed that in my notes. Thank you for that correction. Okay. So we're taking the pole of this guy right here, which is going to be RS plus R sig plus GM RS R sig over RS R sig times CSB plus CGS. So I'm going to do something here just real quick, okay? What's RS over RS R sig? Okay. What's R sig over RS R sig? All right, so we have a 1 over R sig plus 1 over RS. What's GM RS R sig over RS R sig? GM. So we have 1 over RS plus 1 over R sig plus GM, which is RS in parallel with R sig in parallel with 1 over GM, or the inverse of that. So that this is going to come out to look like RS in parallel with R sig in parallel with 1 over GM times CSB plus CGS. And then a 1 simplified form of that pole relationship. Our output pole or really the pole that's contributed by the GM ZY portion of our transfer function is just going to be 1 over RD times CGD plus CNB, right? Sorry, CDB. So we've got our whole transfer function by doing considerable amount of algebra here, and then looked at the transfer function in order to determine our poles, which is the order that we've been doing things previously. Okay. Now what I want to show you guys is that if we just looked at the input node or node X and looked at node Y and saw what resistance was connected to those nodes and what capacitance was connected to those nodes, we would literally get this exact same result, but much quicker. Okay. It's just an alternative way of looking at it. I'm trying to give you guys as many tools as possible, all right? So let's scroll up here. We might literally be able to fit in all of the work that I'm about to do in this little section, or I'm going to try. Okay. So let's look at node X. So what's the capacitance connected to node X? CSB in parallel with CGS. So between node X and ground, CSB in parallel with CGS. What's the resistance seen between node X and ground?
R6.
What do we see looking up? Okay. RS in parallel, R sig in parallel with 1 over GM. So 1 over CX RX would be 1 over RS in parallel with R sig in parallel with 1 over GM times CSB in parallel with CGS, which is exactly the pole frequency associated with node X from our previous exercise. But that was a little bit shorter to figure out, wasn't it? Let's look at node Y. Looking up, the resistance we see, actually, I guess it would be better to do it right here. The resistance we see is RD. Looking down with channel length modulation effects excluded, we see an open circuit because VGS is 0, right? So we would just have RY is RD. Well, CY is obviously just CDB in parallel with CGD. And 1 over CYRY is 1 over RD times CGD plus CDB. Well, there's our other pole frequency with a minimal amount of work. So what I am trying to impart upon you is that when we have a frequency dependence that is associated specifically with only one node, so it's not linked to a separate node, we can figure out what our poles and zeros are pretty easily. Now, let's say, just for example here, that we weren't neglecting channel length modulation, such that there would be a finite impedance between node X and node Y, right? Because our channel length modulation resistance occurs between our drain and our source. Ostensibly, we couldn't then use this technique, but we could absolutely use this technique if we used Miller's theorem to split that resistance R naught to have a portion of it associated only with node X and a portion of it associated only with node Y. Luke, are you raising your hand or are you just fidgeting? So, okay, so if we're looking in through the output node and we look up between this point and ground, we have RD. Can we agree? Okay. So the question is then, why do we see an open circuit looking down, right?
Well, no, I get that, but you're doing it, say, you also take account of one should be able to as well.
No, it should be 1 over GM in parallel with the open circuit, which is 1 over GM. Right? If we were, we did this numerous times, okay? So looking in through the source node with channel length modulation included, we would see 1 over GM in parallel with R naught. Well, with channel length modulation neglected, R naught is infinitely large. So we have 1 over GM in parallel with the open circuit. Anything in parallel with the open circuit is just self. So that's why we see 1 over GM looking up and why we see only the open circuit looking down. Because if we were looking into the drain node of an NMOS transistor with the gate shorted and the source shorted or at ground, we would see R naught by itself. But when R naught is infinitely large, we see an open circuit. And RD in parallel with an open circuit is just RD. I'm not trying to be hand wavy here. That's literally the way to interpret it. Yeah. So we're having, yeah, we absolutely have to consider that VN is grounded out, which is how our SIG here looks in parallel with anything else, because we're determining effectively the resistance or the equivalent impedance seen by this node, or the equivalent resistance seen by this node and the equivalent capacitance seen by this node. So it's very similar to what we did. I hate to tie things back to crap we did in earlier classes, but that's how my brain works. When we were doing parallel and series RLC circuits and all that kind of good stuff, and trying to figure out what the equivalent resistance seen by the energy storage element, we take out the energy storage element, so we open circuit them and look in with our inputs signals shorted out. That's exactly what we did. And then from the perspective of the resistance, we look in and see what our equivalent energy storage element is, which is what this is. So it's the exact same crap we've been doing for 3 years at this point. It's just a new application of it. We're just beating those old horses over and over and over again. That's the great thing. If you have a good grasp of that fundamental circuit theory, all of this stuff is supposed to be pretty straightforward, because it's just the same thing, except, oh no, we've got a transistor now. All right, that is enough out of me for today. Class ends in a couple of minutes anyway. So I have not yet put up your homework assignment on common source amplifiers. I'm going to endeavor to get that finished being written tonight. Would it blow your mind if I gave you a common emitter amplifier on there, so a BJT based circuit, and then made you derive something? Oh, come on, guys.
We might come to your office multiple times.
Okay, that's fair.
My book you will
A lot, I don't know if I'm comfortable with, but we'll figure it out. Okay, I'm going to give you something. Effectively, I'm going to give you almost exactly what we did in the derivation, except with a BJT, and ask you to figure out what the poles and zeros are. It's going to be effectively the same thing, except you're going to have one more small addition to the transfer function because R pi isn't infinite. It literally should be the same thing, except that you'll have another small thing in brackets for the transfer function. Okay, so anyway, so I'm going to give you something like that, and then I'm going to give you actually something that kind of reinforces what we did here. It's going to be a common source problem, so MOSFET, except that we're going to, and I talked about this, I believe, at the end of class, I'm going to have a capacitor and resistor network at the output node, and then I want you to figure out how that contributes to the transfer function, which is literally just do what we did here. Okay. And then maybe one more problem after that. All right. See you guys on Monday. Yes.
What are you going to work with videos?
Fantastic question. All of the videos, except for the one we are literally still in the process of recording, are actually up on Moodle right now.
Because I checked this morning.
I did it this morning after, I want to say I had most of them up, maybe not. Maybe I did them all at 10 a.m. I don't remember, but they're all up now.
I checked last night.
Yeah, I had all but Wednesday's class edited and uploaded to YouTube yesterday, but they were all in draft mode because I went home and then I fell asleep before I remembered to do it. So when I wrapped up my Circuits 1 class, I believe I took them all out of draft mode and put the links on our Moodle page. So they should all be up now.